Hey everyone, my name is Sergey. Doing the AI Masterclass, a little pretentious title, but let's see if it matches the title. Next slide. So about me, I'm right now a co-founder of an AI-powered product studio called Volition, brand new thing. I'd love to talk to you after the presentation about it. Next. And before that, I was the co-founder of Gradescope, which is a web app for grading exams, homework, programming projects. And Gradescope was acquired by Turnitin, where I was head of AI until last year. I'm also a co-organizer of the Full Stack Deep Learning program, which is an educational program for people training deep learning models and trying to ship them to production, most importantly. And I got my PhD in computer science, working on computer vision at Berkeley in 2014. Lastly, I'm on the advisory board of GSV Ventures. And so I help startups in their portfolio or advise them on investments they're considering making. So my goals for this presentation are fourfold. Just define the terms and technology, see what's possible right now with AI, identify some problems that we should watch out for, and lastly, leave like 10 minutes, a quarter presentation just for questions. And let's start with terms and technology. So the most general term is just artificial intelligence. That's why this is called AI Masterclass. But mostly what people actually do right now is called machine learning, right, which is making data-driven predictions. And specifically within machine learning, there's something called deep learning, which is the best method right now for machine learning. And you might have also heard the term data science. And it's kind of adjacent to all of this, not fully overlapping with anything, because it also includes just statistics. So usually when people say AI today, they usually mean machine learning, and they actually usually now mean deep learning specifically. And that's what we'll focus on in this lecture. The types of machine learning that people do are threefold. Unsupervised learning refers to learning the structure of data such that you can generate basically new forms of that data, like maybe deep fakes you've heard, or insights about the data. So here's like a fake product review. So maybe someone malicious is generating a bunch of reviews to post on Amazon for their product. Or maybe you've seen like a deep fake video of Obama saying stuff that he never said, or Tom Cruise saying stuff he never said, and other people. There's also supervised learning, which is this idea of going, can you hit next? Learning how data maps to labels. So for example, you might have a photo of a cat, and that would map to a label called cat. Or maybe you have an audio form, a WAV file, and that actually is you saying, hey Siri, trying to wake up your phone. There's also reinforcement learning, which is this idea of an agent acting in the world to win games potentially, achieve some kind of reward, maybe drive a car, stuff like that. And most famously, I think, is you see like chess playing AIs, Go playing AIs, and just other game playing stuff. But whatever it is, the inputs and the outputs to the AI are just numbers. So for example, the input might be something like a picture of Abraham Lincoln. And so what we see is like clearly just a picture of Lincoln. And then the output might be the word Lincoln. But to a machine, what they would see, can you go next? So what the machine sees is just a bunch of numbers, right? So there's no image, it's just a bunch of numbers. Specifically for this image, it might be the intensity of how black each pixel is, right? So maybe it's like 20 by 40 pixels. So you'll have 20 times 40 numbers, where each number is how black the pixel is. And that's what the machine sees. And then what the machine will say is just another sequence of numbers. Maybe it's the sequence of letters that come to mean Lincoln. So why is this hard? Why is this a research area? Why were we talking about this? So first of all, there's like an infinite variety of inputs that can all kind of map to the same meaning. So for example, if you think a movie's good, you might say, I love the movie. And someone else might say, among the best films of all time. And then someone younger might just type some emojis. And they all mean the same thing, but they're totally different in terms of what the machine will receive as input. Also, like the structure of the world is very complex, and it has structure, but it's complicated to explain what the structure is. So these are two different people in a bunch of different illuminations. So you can see how it looks very different, but we can still recognize it's the same person. We can actually infer that there's a light that's moving around the person. But to a machine, they don't know any of that. They just see pixels. And lastly, meaningful differences between images can be very tiny, right? So this is a Chihuahua or muffin, where some of those are Chihuahuas, some of those are muffins, and it's actually hard to tell, which one's which. Next slide. So how does it work? So the inspiration comes from the thing that we know to be intelligent, which is the brain. And the way the brain works, right, is composed of billions of neurons, so specialized cells that basically take electrical input on one end, roughly, and then if there's sufficient input, they send an electrical output down the other end. And that's a simplification of what's going on, but it's a useful simplification. And the brain itself can be thought of as having inputs and outputs as well. So that's the biological inspiration. And the way that the way the field has formalized this inspiration into actual math that we can do stuff with is modeling a neuron as this thing called a perceptron, which basically is like a mathematical function where inputs are summed with or multiplied by weights, summed together, and then passed through some kind of step function that models like whether it's firing or not firing, essentially. And then putting a bunch of those together, next build, you get the neural network, which is composed of a bunch of these simple perceptrons, but there's millions of them, just like there are millions of them in the brain. Next slide. So mathematically, a neuron is really just a vector of numbers, and the numbers correspond to the weights. So inputs come in, they get multiplied by the weights. What a neuron is basically then just the weights. And the layer of a neural network, which is how they're arranged. Neural networks are arranged in layers of perceptrons, but a layer of perceptrons is just a matrix of numbers. So it's just a two-dimensional table of numbers. And then, next slide. The whole network can be seen as just a set of matrices. And when you see it this way, we call them parameters. So next slide. The point of training neural networks is to find the parameters, which are just all these numbers that define all the perceptrons, that minimize the prediction error on some data. So data might be coming in, maybe it's your height, and that's your input, and then the outcome is the age to which you live. There might be some relationship. If there is some relationship, we can try to train a neural network to predict that relationship. And the basic idea is that the more parameters the network has, the lower we can get that error between our prediction and the actual raw data of the world. So the trick here is, of course, not to overfit on the data, because if the network is like really, really big, then it can just memorize every single data point, and just, if it sees something that's out of distribution, as they say, a data point that it hasn't been exposed to in training, it won't know what to say. But the thing about neural networks is they're really good at actually getting the structure of the data and not overfitting on it. So in summary, deep learning is something that treats inputs and outputs as just numbers. It has millions of parameters, just like there are millions of neurons in the brain. It's trained with millions of examples. So in order to train that cat recognizer, you'd show it literally millions of images of cats and not cats until it gets it. And it takes actually years to train the best models, unless you use specialized hardware called GPUs, graphical processing units, originally for video games, but repurposed for this kind of math. And still, today, the best networks take weeks to train, or potentially months, and on thousands of GPUs. So it's still a heavy lift. And so for that reason, usually people start with networks that are pre-trained, meaning that you took a network, you trained it on some large data set, like ImageNet is like 1 million images with labels. You start with that, and then you can train it on your data, which might be medical data or something specific for whatever you're doing, but you can train faster because the network was pre-trained. So that was basically the terms, technology, and that's a third of the presentation. The next third is going to be what's possible to do with this technology right now. So one field that people have applied this to is game playing, and that's an example of reinforcement learning. So reinforcement learning is learning how to act in an environment. And a simple environment is checkers. There's simple rules, there's 2 players, and that game was actually solved as early as the 50s. Solved as in a computer could play it as well as the best human. Chess took much longer, but in the late 90s, the first IBM AI beat the world chess champion, and it was a big deal. Go took another decade or 2 decades actually, because it's a much more high-dimensional, complicated game. But about, I guess, 6 years ago now, a Google DeepMind trained AI beat the world Go champion as well. And in fact, even 3D video games that are very complicated, such as Dota 2, which is this real-time strategy game, OpenAI had a AI trained that beat the best, and this is even a more complicated game because it's actually 5 players versus 5 players instead of one-on-one. And there's many more actions and so on, but our best AIs are now able to beat our maybe not the best players yet, but pretty good players. In robotics, what we see is, we've had Roombas since like the early 2000s, pretty simple, but they can find their way, they can know when to charge themselves. We maybe have seen demos of robots from Boston Dynamics that can walk on 2 feet, which is actually very complicated, jump, get pushed, and still maintain their balance. Cars that can drive on well-mapped roads in good conditions, like in Phoenix, for example, have existed since like 2018. I think Waymo's been driving in Phoenix since like 2018, recently approved for some parts of San Francisco, which is exciting. Robotic arms that can not only pick up something that is always in the same place, but actually use vision to see where the thing it's trying to pick up is and orient itself to pick it up at a speed that's actually useful for industry, is pretty recent, maybe last year, a company called Covariant.ai. Image understanding is another domain, and that's an example of supervised learning, which is going from data that has labels to, from data to the label. So an example could be this thing that we talked about called ImageNet. There's 1,000 different object categories like go-kart or koala bear, and there's 1 million images. And in 2015, the best AI was actually better than the best human at this task. In 2017, a really good AI can mask out, so not only know that an image contains a koala bear, but draw like a precise boundary around where it is, which is much harder. And even today, an image can be captioned in a way that actually is better than the way humans caption it by a vision AI. So here's 2 examples. And the caption is good, but also this object has never been seen by the AI, so it's doubly impressive. Image generation is an example of unsupervised learning, which is just learning how images are structured in order not to predict what the label is, but to generate a different image. Maybe a deepfake. So there's a website you can go to called thispersondoesnotexist.com, which will just load you like a new human face that doesn't actually, it's not a real person, it's generated by AI. We can transfer a style of a Van Gogh painting to a photograph very convincingly and realistically, and probably better than a person can. We can generate images from drawings. So this is an NVIDIA system where the person provides just some basic input and then goes from that to a pretty convincing photograph that is rendered by AI. And even generate images from captions, so not even providing any visual input, but just saying an armchair in the shape of an avocado, and then getting examples of that kind of image. This is an OpenAI model called DALL-E. So this is very impressive. And it even understands things like a storefront that has the word OpenAI on it. So it understands words, and it can render how a word would look from different perspectives and so on. Text understanding is obviously living in our phones all the time. We can transcribe speech when we talk to Siri, and then Siri talks back. We can translate text between languages. So Google Translate is something that I use quite often. I'm sure you do too. And maybe this hasn't been productized just yet, but it actually does work pretty well now. AI can understand the sentiment, the grammar, is able to summarize what the text is. And in fact, it can do it with one model. There's a paper called T5 from 2020 that you basically give the instructions to the model as text, and then you give text, and the model outputs text. So you can say, translate English to German, that is good. It says, das ist gut. Or you can say, summarize, and then give it a paragraph, and it outputs a summary of the paragraph. And it's able to say, maybe you're able to do a sentiment analysis. Is this a positive or a negative review? And it's the same model doing it, which is pretty freaky. And it gets freakier still when you talk about text generation. I'm sure you've seen the headlines about GPT-3, right? It's learned to code. Next build. It's learned to maybe even do poetry. Next build. And it can write blog posts. So it actually is really good. Here is something I used just yesterday. There's a demo. If you can sign up. You can go to beta.openai.com. You can sign up for the API. I am at the Best Education Technology Conference listening to a presentation titled AI Masterclass. The speaker is, and then I hit submit, and then what you see after that is what GPT-3 produced, and it says the speaker is talking about how artificial intelligence can be used to improve the quality of education. He's showing examples of how AI can be used to create personalized learning experiences for students and help teachers adapt their teaching methods to better meet the needs of their students. And it continues, and it all makes sense, and it's something I very well might be talking about. So it's not text that it's seen anywhere else. If you search for that exact text, you will not find it on the internet. It is actually new text that it produced. And a reasonable mental model to have about exactly how good GPT-3 is that it's pretty good. It just doesn't quite know what it doesn't know. So it's going to sound very confident no matter what it's putting out. And it'll have some facts. It'll have some like fibs. It maybe won't quite hold together, but if you don't pay attention, it'll seem like a totally realistic thing. People have done tests on it, like does it understand logic? Can it do math? The answer is basically like not quite, but maybe sort of, and it's always improving. So what's around the corner then? I think so around the corner, I would say like within 5 years, we should definitely expect to see this. So like GPT-4 will produce really realistic news articles that actually just take some facts and is able to write like an article that reads well, and you will not be able to distinguish from a human writer. So we've seen realistic images. Videos are still not quite there, but I think within 5 years we'll see realistic videos as well. We'll hear music that's just AI generated that seems like great music that we enjoy hearing. And arguably, like some of this stuff is maybe possible today. It just kind of depends on how much cherry picking you do. Like, you might generate a good news article from GPT-3. You'll just have to maybe select some paragraphs and edit it a tiny bit, or you might get lucky. But within 5 years, it'll be reliable. Customer support good enough to fool humans. So if I call someone and I ask for help and I never talk to a human, but I don't actually realize it, I think that's probably possible within 5 years. Maybe not if you go off script. And then full self-driving in like certain cities at certain times. So maybe like not at night, and maybe not in every city in the world, but in some cities for sure. Oh, and then great tutoring in some subjects. So like a really good math tutor, a really good writing tutor, totally possible, even today for some subjects, and kind of expanding out in the next 5 years. What may or may not be around the corner is also interesting. So could we have a car that can drive in Kolkata or on the edge of a cliff and you would trust it? Could we have a robot that just basically acts like a dog, seems to kind of get what you mean, seems to be as mobile as a dog? Could we have a tutor that I can use to learn any subject. Or maybe the tutor would read the textbook for me, and then I could talk to it, and it would teach me the textbook. And these things are really getting pretty close to what we call AGI, which is artificial general intelligence, which is this idea of just intelligence that's as good as humans. And the truth is, no one knows whether the current method that we have, which is deep learning, is going to be enough to achieve any of these things. And if it's not enough, then really no one can give you a time estimate. Like, if it is enough, then it's probably going to happen within, probably the decade. If it is not enough, then it might be a decade still, it might be 25 years, it might never happen, we don't really know. But I think most experts would bet on AGI within like 50 years for sure. 25 years, I would guess, is pretty realistic for most experts. So what are the problems with this? Well, one important problem is representation. So there's some intelligent features that we're developing now that don't actually work for all people. So an example of this is this pretty low-tech thing with a soap dispenser, but actually doesn't work on dark-colored skin. And so there's a tweet of some guys just trying to get it to work, and it just doesn't work on dark-colored skin, and it does work on white skin. And that's obviously a problem. And you can actually experience this in apps that are on your phone, like Snapchat. I mean, I think they fixed it, but you could have experienced it a few years ago, where like a face filter that replaces your fat with that of a cat just wouldn't work for black people. It would only work on white people. And that is obviously a problem of representation. And maybe there's even a larger problem, which is, some of these technologies, do next build. If we focus only on whether these new technologies work for all people, we maybe miss the fact of whether these technologies should work at all, right? So face recognition, huge problem that it doesn't work for all people equally, but also is just a huge problem in itself if we use it without some limits, right? So the current laws, for example, you shouldn't expect privacy when you're in public, right? If you're on the street, you have no expectation to privacy legally in the US. But the new technology that we've developed now kind of redefined what it means to be in public. So now being in public means being anywhere at any time, being on any website on the internet, on any street, in any city with the cameras, in anyone's photograph, which is obviously not the context that we had when these laws were written. So until we update the laws, we should really be careful about working on some of this technology. There is a real potential that these technologies will persist certain biases that exist. So for example, this is Google Translate from a few years ago. And if you type, she's a doctor, he's a nurse, translated to Turkish, which I guess doesn't have the feminine, masculine pronouns, and then take the Turkish and translate it back. Now it changes it to he's a doctor, but she's a nurse, which is probably learned from just the large corpus of text, aka like all of the internet that Google Translate was trained on. But it's a bias that we should be careful about persisting. Now it actually has been improved. So now when you do it in Google Translate in Turkish, it'll actually give you two choices. Did you mean she's a doctor? Did you mean he's a doctor? So this is an example of using user interfaces as a way to improve biases in the model, and very important. And I think it's actually worth walking through an example of like how this can happen. So let's say we have a machine learning model that we want to be able to predict something about a hiring decision that our company is making given a resume. Could be used for multiple things, but so the machine learning model is trained on data, right, as we saw. It doesn't exist in a vacuum, it exists when trained on data. The problem with the data is where does it come, like what is the data? Is it the decisions we made for hiring, or is it actually the performance that the people we hired showed after we hired them, right? If the data is only about the hiring decisions, then we can't say anything about who's a good employee or not, unless we use something about job performance. And the data comes from the world also, right? So we have data at the company, and the company exists in the world, so our data exists in the world. And the world has some known biases. So for example, our hiring pipeline might be biased. Our hiring decisions might be biased through some existing process, probably unconscious. And our performance ratings, if that's what we're using, are probably also unconsciously biased. So then no matter what we pick in terms of like what data we use, well, it's better to use performance of the employee, but that's still not great because even that's biased. Our data is biased anyway, and therefore whatever model we train is also going to be biased, right? And then what are we using this model for? Next build. Is it for sourcing? So we have 1,000 applicants, we want to get it down to 100 applicants, right? That's one situation. Is it for double checking a human decision where we actually have a human in the loop making the decision, but the AI is just double checking them to see if it agrees? Or is it actually making the hiring decision, right? These are 3 different levels of potential danger. But in all of these things, it's totally possible that we're amplifying existing biases. So as AI practitioners, we have to be very conscious about not only is our training procedure biased or not, but also where's our training data coming from? How is our training data generated? How is the world biased? And then what are we using the machine learning model for? Longer term, we have dangers from autonomous weapons. And it's tempting to just say like, well, that's just movie stuff, Skynet, Terminator, whatever. But actually, as they say, the future's already here, just not evenly distributed. Apparently, Israel has deployed autonomous robo-snipers and drones that just, kamikaze drones, basically. And yeah, they obviously raise an ethical dilemma. Then people are worried about replacing human labor, right? So that might be good, right? If we have robotic labor that's cheap and is able to help us achieve our goals, that's probably good because the developed world population is aging. Usually you need a certain ratio of like working age people to old and young people who can't take care of themselves. And this is, for example, the demographic pyramid of Japan, which is projected by 2050 to have more old people than working age people. And so there just aren't enough working age people to take care of the old people. So it'd be great to have robots. But the bad part of that is that our societies are just not set up to care for those who lose their job in the transition from human to robotic labor. Next build. And counterintuitively, I think, and it's becoming kind of expert consensus, that the white-collar jobs will probably be replaced first. So this is Sam Altman, the CEO of OpenAI, which developed GPT-3, for example. And so he expects it to go in like creative fields like Photoshop masters, painters, musicians. They will actually go first because AI is like already pretty good at those things. Cognitive labor like marketing, maybe education, copywriting, yeah, that's probably going to be next. And then physical labor like plumbing is actually really hard because it's hard to operate in the physical world. There's no GPT-3 for the physical world. It's more expensive. You need electricity or some kind of fuel source to power that robot and so on. So somewhat counterintuitive. An interesting angle is like the labor that's low skill. So for example, fast food workers or janitors, stuff like that. It might not be replaced by a robot, but it might be controlled by an AI, which will still feel very, very bad to the people working those jobs. There's an interesting short story called Mana, which you can look up. But basically, if the AI is just hyper-optimizing all of your day and you don't get you get exactly 5 minutes rest because that's the optimal amount of rest, it's not a very utopian future. So education is obviously key to solving a lot of these problems, whether reskilling as people lose jobs, whether educating people about proper deployment of AI, or just getting kids ready to live in a world where they live alongside AIs. Education is key. I consciously didn't cover any educational use cases of AI because I want to leave 10 minutes for questions and answers. So you guys have any questions or thoughts? Yeah, in the back.
That was a fast journey. Thank you very much.
Yeah, thank you. Thanks for coming along.
I find it very interesting that at the border, suddenly machine and humans communicate. So isn't that, or couldn't that have been a model from the beginning? I mean, a car, for example, that asks pedestrians, hey, I will pass by in 10 seconds. I mean, this kind of exchange has not been part of the AI work because it has always been, we want to replace. So isn't the human-machine team approach the better heuristics?
Yeah, that's a very interesting line of thought, which is there's AI, which is artificial intelligence, and then there's IA, which is intelligence augmentation. So I think there's a way of thinking about these very intelligent machines, not as replacement for our intellect, but as augmentation for it. And that can lead to very different ways of deploying them. So yeah, maybe it's not a self-driving car, but just a car that makes it a lot easier to drive. Or I think something we'll have to figure out is if you post a tweet and you see a comment, it should clearly be labeled whether that comment came from an AI or from a human. But right now it's not, and there's no way to prove that it actually came from a human. So we'll have to figure stuff like that out.
Thank you for the presentation. Anne-Marie Sastry from Amosite. Question is this. When we think about education, we think about AI-generated content for education. There are multiple objective functions we can think about. One is, as we do in social media, picking content that is interesting or attractive to the user, which may or may not always be a good thing, given the example of the internet. Another objective function might be information that's useful or truthful or spurs change. When you think about that, how do you think about it?
I mean, for any application, not just in education, it's worth thinking about what are you actually trying to do, right? And how can it be harmful? How can it be helpful? What has to be true for it? In education, for example, the AI that we've developed at my previous company, Gradescope, which was, we called it AI-assisted grading. So it was something that assisted the instructor in grading student answers. So there, the task was to speed them up, right? And so not to replace how they make the decision of how to grade an answer, but to potentially take all the answers that are the same and present them as one, unit to the instructor so they can grade half the class in one go. For generating content for education, I think it just has to be the same. It's like what has the potential to confuse and what can be most edifying. And I think it's totally okay, I guess, I think it's in general good to not use AI to its full potential at any time, but to potentially go only halfway so that there's still room for humans to make some of the decisions in the workflow. So I don't know, that's how I like to think about these things. Yeah. Yeah, intelligence augmentation all the way. Yes, sir.
Hi, thank you for your presentation. I'm an AI enthusiast, and it's relatively simple to understand like the supervised algorithms, but superficially, how do the unsupervised algorithms work?
Well, it's a little bit of a terminology trick. Some of the things that we call unsupervised are actually supervised by covering up some of the data. So like the way GPT-3 is trained, for example, is unsupervised because there's no labels, but you take a sentence and you mask out a random word in it, and then the task becomes to predict what that word is, right? So the data kind of supervises itself, right? Or for vision, you might take an image and then just obscure a patch of that image, and then the task of the model would be to predict what was in that patch that became obscured. So that's usually kind of how the trick works, is it's not truly unsupervised, it's just not supervised by anything other than what's already in the data. Yeah, that's usually the way it is.
Thank you. Maurice Beasley, Superintendent in Clayton County, Georgia. Any thoughts on the pace of change if a human replacement tax is required when AI replaces jobs that humans normally do?
Human replacement tax? You know what? I've actually never heard of that. So I don't have thoughts, but it's a difficult question because, you know, when horses were replaced by motor cars, people were upset about the horse drivers losing their jobs. Obviously, we think today we live in a better world than in the past. Would it be right to tax cars very heavily and like delay their introduction? It's hard to say, you know, looking back from the present. So looking back from the future, what should we be doing today to like ease the transition? I don't know. It's a political question. I think the best that AI people can do is just inform the policy people as to the pace of change, as you said, and that's what I tried to do. Like, what's possible today, what's possible in 5 years, and what's maybe not possible in 5 years. But it's not our role to make policy prescriptions. I think it's all of our role to, I think about what the policy prescriptions should be and suggest them. I just don't think I have any special voice in that.
Hi, great presentation, thank you. I know there's lots of problems and bias, and we all need to be like hesitant and skeptical about just throwing some of these things out at our kids and students. But if you think about K-12 especially, like what's one application of AI that you're most excited about being possible like in the next 3 to 5 years? Something beyond just grading.
I'm still excited about, I guess I'm excited about two things. The first thing is kind of related to grading. It's just everything that takes work off of the teacher's shoulders. So maybe there's something that can listen passively as the teacher interacts with students and measure certain things about how it's going and gives them useful feedback, or identifies students that maybe aren't paying attention or struggling, and which in effect gives the teacher superpowers because now they know how to better engage, who requires special attention and so on. So things like that I think are very good still. And then the second thing that I'm excited about is just the creative potential for some of these tools. So, you know, we showed you GPT-3. I worked at a company called Turnitin. Turnitin tries to detect whether something is plagiarized. Obviously it's a big threat, right? Where now it's like paraphrasing on steroids or potentially even cheating on steroids, where I can just ask GPT-3 to write big chunks of my essay for me. And that's a problem, but seen from another angle, it's an opportunity as well. So like, what is the creative potential for these tools? Should we still, you know, like there's the creative tools of drawing a tiny bit and then the AI kind of auto-completes it to make it more realistic. I just think it's really interesting to just let kids play with that and see what happens, and then help teachers. Yeah. Sure. Yeah.
I have a question. What do you think is like the what limits the progress of AI actually? What's the current limiting factor of huge progress?
Yeah, that's a great question. So there's two possible answers. The first answer is just time and like engineering. So GPT-3 is like several billion parameters. The next version of GPT-4 is going to be probably tens or hundreds of billions of parameters or trillions of parameters. And that's just a scaling problem that is purely an engineering challenge. Like it's using the exact same technique that I kind of gave you a preview of, like everything's a number and you just kind of try to fit to data. If that keeps working, then just engineering effort and time and our compute is holding it back. If it's not enough to reach AGI, then new techniques. But right now, you know, most experts seem to believe that it's just engineering. So I only have 20 seconds left, so probably no more questions. I thank you. Thanks for your attention. Hopefully this was a little bit helpful. If you have any questions, email me, follow me on Twitter. Thank you.